Hi there, so this is the 2013 Scholarship Stats exam and we're going to be doing question 3a. A yogurt manufacturer has developed a new style of yogurt using a different formula. The manufacturer wants to know if customers will be able to distinguish the new yogurt from the currently produced yogurt. A triangle test is used in which a taster tastes 3 samples of yogurt. 2 are samples of the current yogurt and 1 is of the new yogurt. The yogurts are presented in a random order. The taster is asked to identify the sample of the new yogurt. Out of a panel of 15 tasters, 11 correctly identified the sample of the new yogurt. Is this sufficient evidence to conclude that the new yogurt is distinguishable? In your answer, justify the choice of any probability model used. Okay, so the first thing we need to look at is what are the actual instructions we're being given. So what verbs or doing words are directed at us? Well, if we look at the last 2 sentences, we are asked, is this sufficient evidence to conclude that the new yogurt's distinguishable? So that we've got to decide whether the evidence is strong enough to support that theory. And secondly, we have to justify the choice of any probability model used. So in a scholarship exam where the topics are all mixed up, that is a key, isn't it? It's a giveaway that we're dealing with a probability model. So very likely a type of probability distribution. Okay, so how do we get started? Well, let's look at the actual ingredients of the situation and think which distribution would be appropriate here. So pause the video and have a wee think about that and see what you come up with. And the first thing we really need to do is to actually frame the problem. What are we being asked to do? When you're asked to test a claim, as a general rule, use the idea of innocent until proven guilty. So innocent until proven guilty. So in other words, start with the idea that nothing is going on and that the treatment or whatever is being used is not actually having an effect. Start with that idea and see how likely it would be to get the results that they've obtained by chance alone. So what does innocent until proven guilty mean here? Well, the claim is that the tasters can actually distinguish the new yogurt from the old. So innocent until proven guilty would mean, let's start with the idea that they can't, and that the yogurt, and that they're equally likely to pick any of the 3 yogurts and say this is the new one. So let's start with that assumption. So if chance is acting alone and tasters are equally likely to pick any of the 3, since tasting orders are randomized, if this is the case, then how likely would it be for 11 out of the 15 to correctly identify the new yogurt? So we need a distribution model to represent the situation where you've got 15 tasters and each taster is being given 3 yogurts, one of which is the new yogurt, and has to choose which one they think it is. So let's think about which distribution that could be. Firstly, are we dealing with a discrete or continuous variable? Well, the answer is a discrete variable because we're counting how many out of the 15 tasters correctly identify the new yogurt. So it's whole numbers. So it's discrete. So then we think, well, binomial or Poisson? Well, we're counting the number of tasters that correctly taste it out of a panel of 15 tasters. So it's out of a fixed number of trials. So it can't be Poisson, has to be binomial. So for binomial distribution, we need parameters. What are our parameters for binomial? Well, they are n, the number of trials. So that's going to be 15, isn't it? And then p, which is our probability of success in each trial. Well, success is a taster picking the correct one when they say, oh, this is the new yogurt, and they get it right. So if the yogurts are in fact indistinguishable, what are the chances that they happen to pick the correct yogurt? That they fluke it? Well, of course, it's 1 out of 3, isn't it? So 1 out of 3 is our p-value. Okay, now we need to test the probability of getting the results as extreme as what they've obtained by chance alone. So they got 11 out of their 15 tasters correctly identified the sample. So do we need to test the probability that x equals 11? The answer is no. We actually need to test the probability that x is greater than or equal to 11. Why? Well, if we tested just the probability of x being 11, so exactly 11 getting it right, that'd be kind of like me saying, well, what's the probability that if I toss a coin 100 times, I get 51 tails? Now, if I tossed the coin 100 times and told you I got 51 tails, you'd believe me, wouldn't you? That would sound quite reasonable, because 51 is very close to 50, and we expect about half of the 100 trials to result in tails. But if you looked at the probability of exactly 51 tails, it'd be really low. It'd be low because that's only one outcome out of about 100, isn't it? And so if you wanted to test 51 tails out of 100, how reasonable that is, you would test the probability of getting at least 51 tails, wouldn't you? And it's the same here. We need to test the probability of getting at least 11 out of 15 people identifying the correct yogurt. So, just writing that up. So what are we doing? We're testing how likely it would be to get the observed results of 11 or more correctly identifying the new yogurt by chance alone. There is a fixed number of tasters, n equals 15. Two possible outcomes for each taster. Correctly identifies which is the new type of yogurt or does not. So, a binomial distribution can therefore be used to model the number of tasters, x, out of 15, who correctly identifies the new yogurt. So we need to calculate the probability that x is greater than or equal to 11. So grab your graphics calculator and see what you get. So menu distribution, menu stat distribution, binomial BCD, variable, and obviously we can't work out greater than, we need less than or equal to. So the less than or equal to value that we're going to be dealing with is, it's going to be 10, isn't it? Because we want to find out the probability of 11 or more. So 1 minus the probability that x is less than or equal to 10. So maximum x value of 10, num trial 15, p value 1/3. And we get 0.9981982. So let's write that down. Good, so now we subtract that from 1 and we get our answer of 0.00181. So what do we make of that? Well, it's very low, isn't it? In fact, if you look at that, 0.00181, it's only 1 or 2 out of 1,000. So it is very low. So what does that mean in terms of our question? Well, the original problem was to try and work out how likely it would be to get results as extreme as 11 out of 15 by chance alone. So the answer to that is that if the yogurt was actually indistinguishable and the tasters were just fluking it, the chance of as many as 11 or more out of 15 correctly guessing it by chance alone would be only 1 or 2 out of 1,000. So if you repeated this experiment 1,000 times, you would expect only once or twice on average would you get results like these. Hence, we can say it's very, very unlikely to occur by chance acting alone. And that's a good statement to kind of, I don't know about memorize, but certainly it's a good wording. It's a good way of actually concluding this. Verdict. This provides very strong evidence that tasters tend to be able to tell the difference between the taste of the new type of yogurt and the old type of yogurt. So we've answered the question. Now, what else were we asked to do? Well, the very last sentence tells us, in your answer, justify the choice of any probability model used. So we do need to make sure that we've justified why we've used binomial. Well, a good way to remember the 4 conditions needed for binomial is a kind of a phrase, International Fight Club 2. In for independent, international, fight The F stands for fixed number of trials, International Flight Club. C stands for constant probability of success. And then 2 for 2 possible outcomes in each trial. Now, we've already covered a couple of those. We've described back at the start that there is a fixed number of trials, or fixed number of tasters, and we put that in context by using the word tasters, which is important. If you just said trials, you wouldn't get the marks. So we've said tasters. 2 possible outcomes for each taster. Correctly identifies which is the new type of yogurt or does not. So we've put that in context. So the other 2 to look at are independence and constant probability of success. The use of binomial here assumes independence between the tasters. So what that means in this context means that their choices are assumed to be independent of each other. We should check that the tasters themselves are not linked in any way, for example, from the same family, class, or interest group, and not able to communicate with each other. The other assumption that we're making here is the constant probability of successfully identifying the new yogurt. Now, this should be satisfied because we're told that the tasting order is randomized. And so when we link this to some of the ideas from experimental design, when you've got treatments, because in this case the treatment is where the tasters are given the yogurt and taste it. So the treatment order should be randomized. Why is that so important? Well, it just avoids the risk of any order effects. If all of the tasters got the yogurts in the same order, it would be possible that the first yogurt they taste might kind of obscure their judgment for the remaining ones. So if one had a stronger taste, it might affect whether they're able to distinguish the other 2. So that's really important. Okay, so let's have a look at the marking schedule. So judgments. Note, can work out the probability that x equals 11 as 0.0015 and make comment about its value being highly unlikely. I think they're being very generous here, aren't they? Because really, as we talked about before, the probability of any particular x value is always going to be quite low. So really much better to do what we did and look at the probability that x is at least 11. Second, confidence interval approach is incorrect as n is small. So we're only doing 15 trials. Third, binomial can be justified with at least 3 conditions in context. So notice you had to have at least 3, and they had to be in context. Judgment. So the maximum here was S. Now, if you're not familiar with the scholarship marking schedule, have a look at it on the NZQA website under the 2003 assessment schedule. The maximum grade you can get in a scholarship question is O for outstanding. Here, it didn't go that high, so the maximum here was S for scholarship level. An appropriate conclusion is provided with correct evidence along with binomial model being justified. So you have to have the right conclusion, back it up with evidence, and justify using binomial. P for partial, which means you got some marks from it. Partial credit. An appropriate conclusion is provided with correct evidence or the binomial model is partly justified. So you see how if you forget to read the instructions in the question and forget to justify that binomial distribution, you really miss out on marks. So it's important to really take your time and read all the verbs in the question carefully. Cool. Thanks for listening.